My name is Andrew Theurer. I'm going to talk about improving performance, specifically out-of-the-box performance. I want to cover a few topics here. Current benchmarks, what is out-of-the-box performance, how we do some analysis, and how we're improving the out-of-box performance. And we'll go through some test results and see how well this works. Current performance, when you look at industry standard benchmarks, KVM is doing extremely well. A year ago I was here and I reported on the very first SpecVert benchmark, which was published by IBM. We used KVM. It was sort of by default the best result because it was the only one. In fact, it took a couple months for anyone else to publish a result that was comparable. So 12 months later, we have lots of results in this benchmark, anywhere from 12 core systems all the way to 80 core. And I'm happy to report that KVM has pretty much a #1 position in almost every category there, 12, 16, 20, 40, 64, and 80 core systems. So almost across the board. I think the only one we're missing is 32 core system, where we have a leadership result for SpecVert. And SpecVert is it's a server consolidation benchmark, involves consolidating a number of servers into virtual machines. For example, the 80 core result has 432 virtual machines on one system. KVM scales extremely well today on large x86 64 servers. That 80 core system has 2 terabytes of memory. KVM will run on as much as 4 or more terabytes of memory today. And of course will scale to just a really high number of virtual machines. With benchmarks like this though, it usually goes through an awful lot of tuning, a lot of practice, and make sure you get the absolute best result. Most of these are driven by companies who want to showcase their solution. So they want the absolute best result. 1% is important. It's worth working on for weeks to get another percent. And that's just the nature of industry standard benchmarks. You want to get the absolute best number you can. You'd be really surprised at just how much effort goes into tweaking it and perfecting it. This is a little different from what, say, the average user would do, and what I would call either like out of the box or ad hoc type performance testing, where you would install KVM, install some virtual machines, run your test, get a number, and that's what you get. And maybe you'll do it on another hypervisor, and you won't put much care into hyper tuning what you're doing, because a lot of people just don't do that on a day-to-day basis. Now, there have been some improvements in KVM to make this better. Things like libvirt will ask you what type of guest operating system you're going to have, and if you select the right one, it will provide you with default options that are things like virt.io instead of IDE, which had libvirt not done that, or virt manager, that's generally a pretty common mistake to make for like a user to pick IDE or pick a Realtek adapter or E1000 over virt.io block and virt.io net. So a lot of those problems are pretty much out of the way. There are occasionally other issues. A user may be compelled to pick or build a configuration that's just unrealistic, and it's just an enormous amount of memory. I mean, there's no real hard limit on what you can select for memory. I mean, there are some practical limits, but if you have 2 gigabytes on a system, there's nothing stopping a user from selecting, say, 8 gigabytes or 10 gigabytes of memory. Same for CPUs. People often think bigger is better, so instead of picking 1 vCPU and seeing if that's enough, they might pick 10 or 15 or 20 and just assume that they'll need it, when in fact they probably don't. So there's still some issues there. It's mostly education though. Some other problems are that if you want the absolute best performance, the configuration is not obvious. It's like SRIOV and PCI pass-through. If you wanted the absolute best networking, PCI pass-through is probably your best option today, but you'd have to have the insight in picking the right adapter, and once you do, it's not just selecting it, it's actually loading the right module options to get virtual functions, figuring out where they are, and then through Virt Manager or something else, picking them, not making sure. Sometimes the virtual function driver might load automatically in the host, and you may not seem accessible. So these things are possible for people to do, but it's just a little less obvious. I'm actually not going to talk about that either. The thing I want to talk about today is the performance impact we're seeing by lack of NUMA optimizations for virtual machines in KVM. And in fact, if you attended Andrea's talk yesterday, this is a very similar problem statement as what he was talking about. So let me give you an example here. I took KVM, installed 40 virtual machines. They're all 4-way with 2 gigabytes, so they're not ridiculously large in their configuration. And I ran a benchmark on them simultaneously called dbench, which is a file system benchmark. I chose to run it in tempfs because I really didn't want to bring I/O in the equation here. And it's installed on a 4-processor Westmere EX server that's 40 cores, 80 threads. Pretty powerful, pretty recent server. Used sensible configurations, made sure we used pair virtualized I/O, no special optimizations. Also did this with what I call the mystery hypervisor, which is another hypervisor, and just ran it. And don't ask me what it is, it's a mystery.
x86 hypervisor.
It is an x86 hypervisor, yes. So it's on the exact same hardware, just different installation. And what we have here is the aggregate throughput from dbench. And I was pretty shocked at the difference here. KVM, 14.5 gigabytes a second, and this mystery hypervisor almost 23. That's a pretty massive difference. And looking at trying to explain why, one of the first things we do when we see a problem with KVM is we usually go to the traditional tools for performance analysis. And more often than not, we first look at hypervisor overhead. So we will run something like, might start something simple like top, where you can see a breakdown of kernel versus user versus guest, I/O wait, and idle. And this is on the host. And generally, we would want to see if there's a problem. We first look for an excessive CPU usage by the host and not by the guest. And you would see that usually in kernel time, but you could also see it in user if there's excessive time spent by QEMU. In any modern kernel, you should have CPU counting that attributes for guests specifically. In this case, we had 97% guest and 3% host. That's generally fantastic. You can get a little bit better in that, but that's actually really, really good. So we concluded that it's really not a hypervisor problem here. The next thing we looked at was what NUMA was doing. And this system has 4 NUMA nodes. So there's 4 processors, and there's 4 memory controllers. And Linux has gone through a lot of development to optimize for NUMA. The scheduler has been optimized, the kernel data structures have been optimized, a lot of work has gone into making that as good as possible. So we were hoping that this wouldn't be a problem. But when we started looking around, and this is one of the areas, we saw some evidence that there's a problem. What we have here is in /proc, and then your process ID for a QEMU process, and then the file NUMA maps. It will show you every single mapping for the QEMU process, and it will show you where it's mapped in, so the number of pages per NUMA node. If we had fantastic NUMA policies, we would probably find each of these using maybe one NUMA node and not the others. But what we're seeing is that for any of these guests here, I don't think there's a single one that has maybe much more than 50% of its memory in a single NUMA node. They're generally spread out everywhere. So what happens there is you don't have any central place where the memory is located for the virtual machine. So wherever you happen to be running, and if you're accessing memory, you're generally accessing memory all over the system. Well, the interconnect between the processors provide that channel to get to memory that's from another NUMA node. Those can be saturated at some point. And when you have a situation like this is what happens. So why did it get scattered in the first place? It's mostly due to the CPU scheduler in Linux. And the policies we have today are, I would say, fairly simple and elegant, and they work extremely well for a short-lived process. They also work extremely well for a process that execs and is not multi-threaded. And the reason why is that our initial placement for a new task goes to a least loaded node, so that's generally good for something that's exec because it's essentially brand new. Other issues here, idle CPUs tend to aggressively look for other tasks to steal. So if a CPU goes idle, it will start looking for other CPUs that have more than one thing to work on, more than one task to run. And that's a problem. It can take things away that were, say, running node local. You also have periodic timer-based load balances that do the same thing, mostly for fairness. Now, in both of those, the scope at which they can steal from becomes increasing over time. So most frequently, it's a very small scope. It's usually like CPU sibling threads, core sibling threads. And every so often, it will be all the threads or all the cores. And eventually, it'll be every CPU in the system. So the longer you have a process running, the more likely you will get moved a further distance. And this is a particular problem for a long-lived task. So if you have something like a kernel compile, the chances of that happening are very, very low because each process is basically an exec, run GCC or link or something. It's fairly quick and you go away. But with a virtual machine, you have a multi-threaded process. Most of the threads are probably vCPUs, and they're going to run for a really long time, days, months, maybe years. And so those load balances tend to scatter those tasks, in this case, vCPUs. When that happens, the vCPUs, as they fault in memory, they tend to fault in memory wherever they fault in memory by default where they're running. So if they are scattered, now you start faulting in memory all over the system. And that's really the core of the problem, is that we don't have any policy to herd the vCPU threads and keep them in one part of the system. And we really we also don't have a good way to influence where the CPUs run based on where their memory is located. And it's sort of like a self-serving problem. Like if the CPUs get scattered, well then the memory is scattered. Well then even if you had a policy to favor an area of the system where your memory is for the process, well if the memory is everywhere, it doesn't matter. So it's kind of like a catch-22. So what I've done here is a pretty simple proof of concept. It's a user space balancer. It basically takes over some of the responsibility of the kernel scheduler, specifically for virtual machines. It works off C groups, specifically CPU sets, which is actually incredibly convenient because if you're using libvirt and you have C groups mounted, like C groups CPU set file system, this will just automatically work. What we do is we monitor C groups, we discover new virtual machines, and we do an initial NUMA node placement. And then every so often, we analyze, based on the CPU load of all the NUMA nodes, what kind of imbalance we might have, and then we rebalance. Now, when we rebalance, that means moving the tasks for a QEMU process and its memory. And this is why the CPU set C group is so important. This is all just done extremely well through its interface. I mean, it's very convenient. You can literally just echo a value for the CPUs you want into a file, and you can echo a value for the NUMA node for memory migration. So when you do that, literally all the memory in your process will be moved from one NUMA node to another. It's very simple, and I understand very widely used for high performance computing on really large systems. What we don't do right now is we don't handle really large virtual machines, and mainly because they wouldn't fit in one NUMA node. And with CPU sets, you could specify multiple NUMA nodes, but then you're just scattered across multiple nodes. So it's not really the best solution. What we really want is to redefine the virtual machine so it has a virtual NUMA topology, say 2 NUMA nodes, and be able to schedule one part of it in one NUMA node on the host, and maybe the other virtual NUMA node on another physical node on the host. We don't deal with memory capacity issues right now. So if you're balancing on CPU load, that's fairly simple, but at some point you really need to take into memory capacity, because just because you want to move a virtual machine from one NUMA node to another, you can do that, but if the memory is not available, you're going to run into problems. You probably won't be able to migrate all the memory over. All right, so this is the basic algorithm for this script. If we start up here, you can start this program at any time, and it will just scan for any of the new, or any directories, essentially, in this C group file system. And each group or directory represents one QEMU process. If you find a new group, we have to decide where it runs. The deal is, though, the virtual machine's really not doing anything yet. You've probably been running for maybe 5 seconds. You're probably in the grub bootloader, or initial stages of booting. So there's really not a good way to pick what NUMA node to run it on the system. So we just randomly pick one, because there's really no point in trying to make an intelligent decision at this time. The good thing about detecting the guest sooner rather than later, especially if you just started the guest and this thing's scanning every 5 seconds, is that it actually hasn't faulted in a lot of memory. So picking a node and placing it there is very lightweight, because you might only have a couple 100 megabytes of a guest that's faulted in, and so moving it is relatively painless. We have an interval here. I put 5 seconds here, but it's really configurable. At that point, after we wait, we collect some system utilization data. System NR running, that's the total number of runnable or running tasks on the system, and that's in proc stat today. Per node NR running, this is the number of running tasks per NUMA node. That's not in proc stat right now, and I've made a very small patch to provide per CPU NR running, and based on topology information in sysfs, you can figure out which CPUs are in a node, and then you can read proc stat, and there's a line for every CPU, and now we have a column for per CPU NR running. So you can calculate per node NR running pretty easily. The load for these two are just the NR running divided by the number of CPUs, in this case per node CPUs and per system CPUs. So if you do happen to have nodes that have a different number of CPUs, we're going to make sure that we compensate for that. Next thing we do is, let me back up. This is to establish what sort of imbalance we have. So if you have one NUMA node that has 30 runnable or running tasks, another one is 0, you know you got a problem. Additionally, for each NUMA node, we look at every VM running in the NUMA node, and we get the VM's number of runnable or running tasks. And what we do there is look at the directory for the C group here. We get the task IDs. We read proc, PID, and stat, which will provide a state for that task. In this case, R for running or runnable. And we can calculate how many threads are actually running for a VM. So in general, if you had a 4-way VM and all the vCPUs were running, you would have at least 4 running threads for that QEMU process. You might have a little more because you might have other threads doing work for like I/O and stuff. At this point, we identify the node which has the highest and lowest NR running because we want to correct this imbalance. After identifying that, we have to make sure that all 3 of these conditions are true. And it's important to make sure all 3 really are true. The first one is that the number of running tasks in the high load node minus the load node is greater than or equal to 2. And the reason we do that is that, let me give you an example. If one of them is 44, that's the low one, and the high one is 45, if we decide that we want to correct that imbalance, pulling one over from 45 to the low node, well, now we just sort of reversed the problem here. One's 45 and one's 44, and if we keep doing that, we would just balance back and forth all the time. It's actually the same thing we have in the kernel scheduler today. We avoid just flipping back and forth, moving tasks back and forth. The second one here, this is the high load divided by the low load. So the load we have, which is the number of running tasks divided by the number of CPUs. We divide those two, and we're looking basically for a ratio here. We're looking for a greater than 10% difference in load. This is more about fairness. So if we are above that ratio, we want to correct it. Last one is the load for the high node has to be greater than 1.0. And what that means is that the number of running tasks has to be greater than the number of CPUs. And you could probably get away with not doing this, but the point of this is that we don't want to needlessly balance all the time. And if we're not saturating the CPU capability in a NUMA node, don't bother doing anything at all. Now, with taking memory capacity into account, that's probably going to change, but strictly from a CPU load point of view, we're trying to do as little balances, or as few balances as possible. And so as long as that node isn't saturated, don't bother. So if all 3 of those are true, we pick a VM from the high loaded node and we move it to the low load node. This is all done through CPU sets. You're basically identifying, the directory which corresponds to the QEMU process that you want to move. You're echoing a list of numbers for CPUs that are the new NUMA node, and that's to migrate the tasks to the new CPUs where they run. And for memory, you're just going to echo a value, which is the NUMA node number, to migrate the memory. Now, this.
What migrates the memory?
I'm sorry?
What migrates the memory?
The CPU sets C group actually does the memory migration for you. So there's no system call involved. It's all done through virtual file system. Yes?
Where do you get all the information from? Load, load, and system load? Is it from /call?
Yeah, yes. So for NR running on the system in procstat, that's there. Now for per node NR running, that wasn't there. So I have a fairly small patch that adds that per CPU. Now, once you have it per CPU, you can go in sysfs and look in topology, and for say node 0, you can find out which CPUs are in node 0. Then you can find out which lines in procstat that you need to gather that information. Let's see here. Let's go to the next page. And if it's the one I'm thinking of, it's going to be very hard to read. No, it's not. All right. This is the one after this. OK, so again, I ran this test, 40 virtual machines running dbench. Here's our mystery hypervisor. Here's without the balancer. And here's with the balancer. So we have a 29% improvement in performance here. Additionally, I ran manual binding. So I know I have 40 VMs. I have 4 NUMA nodes. I just chose 1 through 10 go on the first node, 11 through 20 go on the second, and so on. I know that this should be For this particular test case, the best we could hope for to achieve with a balancer. And as you can see that we're awfully close to the manual binding scenario here, within what, a couple, 100 or 200 megabytes a second. The thing is that this test honestly isn't that challenging because of your initial placement and you're randomly placing the virtual machines on the nodes, you get it almost right. You don't get it perfectly right because the random placement is not going to get exactly 10 VMs at one node and 10 in another and so on. But it gets it very close. And the next chart, I'll show you how many balances we needed to do to get it balanced. Some perf stats here. There's a way to program perf to give a performance information on what I call off-node memory accesses. This is when your data is not in your last level cache and you have to access the memory, but in this case, it's specifically accessing memory that's not on the local memory controller. You have to get it from another processor. Without the balancer, we're just off the chart here. This is 217.6 million accesses per second. With the balancer, down to only 6.2 million accesses per second. So a very significant drop here. Manual binding, even lower. And that's probably lower because the initial placement is not perfect. There had to be some balances done at the beginning of this test case. But the interesting thing is, on the instructions per cycle, the number of instructions we can execute per cycle is about the same for the balancer and manual binding. What I take from that is that you don't have to completely eliminate cross-node memory accesses or cross-node communication. You just need to get it below a certain level to make it acceptable. There still will be some increased latency going from one NUMA node to another to get memory. But if you keep it at a minimum, you're probably not going to saturate the interconnect. So,
did you track down what's causing that? I mean, is it like maybe I/O or network because you're spread across all the nodes?
Well, it's basically because, let me go back here. It's because of this, right? Without the balancer, you've got memory everywhere for every VM. And dbench is a fairly memory-intensive benchmark. So your vCPUs are really running all over the place. Your memory's all over the place. And you don't have the convenience of, if a vCPU is running a node 0, it happens to be accessing the memory it needs from node 0. It could be anywhere. All right, this is the chart that's hard to read. This is the output from the VM balancer. And about every 5 seconds, it provides a status update of what's going on. And here's at the beginning. We have the number of running tasks per NUMA node, and then in the system completely. Then we have the number of CPUs in each NUMA node. In this case, it's the number of CPU threads, so we have 20 per node. Then we have the load, which is just one divided by the other. We have an imbalance, which is sort of the ratio of loads. And then finally, we have the VMs that are running in that NUMA node and how many tasks are running. So in most cases, these are 4, because we have 4 vCPUs and the benchmark is running all out. And once in a while, we'll see 5, because there's some other QEMU thread that's doing something. But it's pretty rare to see that, but if we, say, had a network-intensive workload, we'd probably see a lot more of this, or like a disk-intensive workload. As you can see, the number of VMs per NUMA node are not equal here. The random placement didn't get it quite right. But over time, as we move down, you'll see that we get to an even number of VMs per node. And the imbalance is fairly low, and the load is fairly even. This information here is basically the criteria that we're using to decide if we're going to load balance. So the load ratio, the low and high loads, and the difference between the number of running tasks. This is my first crack at this, so I put as much information as I could to make sure the thing was actually working correctly. All right, so that test was fairly easy, and it really didn't exercise the load balancer very much. So I wanted to come up with something a bit more challenging. And unfortunately, it didn't close the gap completely between the other hypervisor. And honestly, there is more work to be done, but it's probably outside of this NUMA optimization. And I'll get to that in a little bit. So what I did was, instead of using 40 VMs, we used 20. And I specifically picking the 20 that are on the first two NUMA nodes after the balancer's been running this first test, because I want to see how well it can do moving half of those to the rest of the system. So when I'm only running those 20, the remaining 20 are idle. And that's the biggest imbalance you can get, other than maybe putting them all on one NUMA node. So we have 20 VMs. We need roughly 10 of them to move to the other NUMA nodes that aren't, they have VMs, but they're not really actively running. So that's what I've done here. This is the mystery hypervisor. I did the same situation there. I made sure that the 20 VMs it had were on the first two NUMA nodes. This is without the balancer. It's kind of what we expected based on the previous test, and with the balancer. And in this case, we're actually slightly outperforming the mystery hypervisor here. So, good news. And it's a pretty challenging test, because you've got to identify and move 10 virtual machines over to these nodes that aren't doing anything. Again, the perf stats, sort of ridiculous number of off-node memory references here, a bit lower for the balancer, and then the manual binding is quite a bit lower. A note about the manual binding. I picked, again, 20 VMs on the first two nodes. I didn't change the manual binding, so they never get to move. And the reason I did this is I just want to show that a lot of times manual binding doesn't work. If your workload is unpredictable, you can't rely on it. So if you're going to use manual binding, you really need to understand what's going to happen on that system. And this is what we would expect, right? Half of the NUMA nodes were being used, and half of them weren't, so we got about half the performance. Quick summary here in the tests. Performance is up by 29%. The optimization is really not that difficult for this test. Pretty much the same throughput as manual binding. We still have another 29% to get parity with the other hypervisor. In this particular test case, the CPU is overcommitted. I have a feeling that's at least a good part of the problem here. The amount of time that the vCPU can run without being interrupted probably affects the cache warmth. So I think we need to look at that. However, when you start increasing the vCPU runtime, uninterrupted vCPU runtime, you tend to increase the probability of lock-holder preemption. We've seen this with KVM on the older scheduler, where the default time slice was around 100 milliseconds. Here we're running uninterrupted, I think, between 2 and 4 milliseconds. With 100 milliseconds, we saw all sorts of problems with lock-holder preemption. So we have to be careful and not just bump up the uninterrupted runtime here without making sure that either the lock-holder preemption solution works extremely well, or possibly a gang-like scheduling algorithm where the vCPUs of a VM all run at the exact same time. The 20 VM test, out-of-the-box performance was improved by 26%, and we have performance parity. There's actually a lot more work to do here. We have to factor in memory capacity and memory imbalance. Even if there's not a CPU load problem. So if you had 2 virtual machines in one NUMA node, they weren't using all the CPU, but they started exhausting the memory. You might actually want to place one on another NUMA node just to give it the room it needs so they can each have node local memory. Other issues involve where you are balancing for CPU imbalance, and you want to take one virtual machine and place it in another NUMA node, but there's no memory. So what do you do? I mean, you actually have to take something out of that other node and put it in the node you were moving from. And ideally, you would probably find a virtual machine that wasn't running at all, it was just using memory. That way you can sort of do a swap for memory capacity, but move the CPU load to the node that's less loaded. Rebalance for optimizing KSM. KSM is a bit of a problem. Yes?
Yeah, I was just going to say, is that really, the suggestion there is not hugely realistic if you've got VMs, KSM across your entire box. KSM is actually actively working against it.
Yeah, it's, this is really.
It doesn't have to.
Yeah, you can kill it. I mean, but if you actually share mappings, and you have to share mappings on a per locality per basis.
It's trivial to extend KSM to do all of the scanning per NUMA node. So you wouldn't get quite the same density because you divide the problem by NUMA node, but it's not at all out of the scope of KSM.
There's always going to be a trade-off of resource consumption versus performance.
But I think if you're scanning globally, I think you're right that it's difficult to probably optimize for this because it may be dynamic enough that you really can't keep up with the page consolidation. And if you have a lot of page consolidation, it's global, it's kind of hard to keep it node local. If you have, say, a lot of VMs who have sharing the same page and they can't all fit in the same NUMA node. But then you just may opt for per node KSM algorithm and you just decide, look, fine, we don't get quite the coalescing that we expected. But
it decreases by the factor of the nodes. It's a significant decrease in the efficacy of KSM, either way.
The other thing you run into is if you're having KSM scan just local per node and you start rebalancing, you're going to spend a lot more time scanning and using up resources that way. So is the benefit really there?
Yeah.
yeah, I don't know. I think it's going to be highly workload dependent, and it's
It's there. Because the scan rates aren't that expensive, and the vast number of pages that are consolidated are 0 pages by about 8 orders of magnitude. So you're going to get good consolidation. Your consolidation rates won't look that different. We're getting way more 0 pages than interesting text pages.
now if they are 0 pages, maybe we're just not even using them anyway. So maybe it doesn't matter that we.
Windows issue.
That's true.
Just don't run Windows?
That works for me. Customers don't always agree.
Were there any other questions before I continue? All right. VM migration probation period. This is because, let me go back a couple slides here. And if you look at these times here, this is how long it took to have the memory migration complete for a guest. And they're on the order of like 4 or 5 or 6 seconds. That's an awfully long time. So if you're going to do that, it's like you want to really commit to it, and you want to be certain that it's important that you do it. So if you're trying to correct for a CPU imbalance, what you might want to do is just temporarily move the tasks for the QEMU process where they run on the CPUs, but not move the memory, and wait a little while to see if that's actually something that's going to be long term. Because if a virtual machine starts running a lot, but then stops after, say, 5 or 10 seconds, then you're doing an awful lot of work to move it and then really not really benefiting anyone because it stopped doing its work. Another way you could do this, sure, go ahead.
You could try setting the memory policy to preferred instead of default, which will, and leave wider open scheduling policies. Maybe update the CPU sets a little less frequently, because then it will prefer to allocate memory from a NUMA node and only go elsewhere when you're strictly out of memory. So you kind of get the home node memory portion, and every so often with overcommit CPU, you can migrate off.
Yeah, if the memory's not already completely faulted in, then yeah, I think that would work. But I think if we're dealing with a VM that has most of its memory faulted in, we can't really benefit from like a fault-in policy, right? Because if it's already somewhere, the only way we're going to get it moved is by like manually moving
Right.
it.
It's part of starting up the VM is
Yeah.
set the policy, bind it to, not hard bind, but loosely bind it to a node.
Sure.
It's worth trying to see what happens.
Yeah, yeah. In fact, I think we're going to really need to do that because I don't think we'll be able to correct quickly enough for memory capacity issues anyway. And we don't want to QMU or whatever because it ran out of memory in one particular NUMA node. So, one possibility is to do that. The other way is to lazily move the memory. But this is actually, so memory that's already faulted in. That's actually can be done. I know someone from HP has some patches on this, but it involves removing all the mappings for memory and then basically refaulting everything in. It's very expensive, especially for virtual machines, because now we're taking VM exits just to touch memory. So maybe we don't do that, but maybe we change CPU sets to set a rate at which it moves memory. So it's sort of a more graceful, slow rate instead of as fast as it can. Let's see. Yeah, when we move a VM, it'd be nice to find one that matches our CPU usage but has the least memory faulted in. Again, because we want to lower the cost of moving the memory from one node to another. So if you can find, say, several VMs that match the number of runnable tasks you need to cure the CPU imbalance, one of them has 200 megabytes of usage and one has 2 gigabytes, let's pick the one with 200 megabytes. And the last one here, handle really big VMs. There's honestly a lot of work to be done here to make this work. It's not just VM balancer work, but it's a lot to deal with, I think, infrastructure with QMU and having correct NUMA topology. Like, it's not just about providing topology to the guest itself, but actually mimicking that topology by having a separate memory mapping for memory allocation for one NUMA node and another for the different NUMA node. But even if you do that, we need the ability, if we continue to do this through user space, to actually migrate specific mappings and not everything as we do in CPU sets right now. Let's see. Let's go on here. Which brings me to my other point, kernel or user. I did this in user space because it was fairly easy to do and trivial to do. I probably could have done this in kernel, but I didn't think I had enough time. And it's honestly just a lot easier to test in user space than in kernel. There are some definite advantages of doing this in kernel. I think we could react much more quickly to problems. The load balancer code in the kernel can do things that we can't do, like when a CPU is newly idle, it can make decisions on what to do. We really can't do that well from user space. If we do this in kernel, we perhaps might as well do some other things that we want to for virtualization. I'm not saying we need a new scheduler class, but it's a possibility. The cons I see are, historically, it's kind of difficult to get big changes into the kernel scheduler. It's usually followed by a lot of risk and an awful lot of testing. So when we moved to CFS, I know personally, from within IBM, we had an awful lot of work to do to make sure it did the things we expected it to do, or the things that we expected of the previous scheduler. So it's risky. And whenever you change something in a scheduler, you're affecting everybody. And that's a big, big responsibility. If you do this in user space, if you don't like it, turn it off. And we can target virtual machines only and nothing else. Or we can target everything that's in a CPU set or C group. So we have some flexibility there. Questions?